Hello and welcome to related rates. So we are finally getting to related rates, which is, as I've stressed, is a very difficult topic, at least in this first half of calculus. It really implies a lot of implicit differentiation. So for this warm up real quick, you're throwing a ball upwards. Is the rate of change of the height positive or negative? Because we're throwing it upwards, that means we're going to have a positive rate of change. And when we're throwing it downwards, that means we're going to have a negative rate of change. Obviously, we can also talk about the fact that as we're throwing it upwards, this ball is going to be concave down. And so if we're looking at the rate of change of the rate of change, it's actually going to be negative, right? Because it's concave down, um, that means that our second derivative is negative. So if we want to call f like the position, f prime prime is the acceleration, and that is going to be negative. The reverse is going to happen if it's downwards. It's not really going to be like a concave up, but for our purpose at least. But if we were to kind of draw the like second half of this imaginary graph, it would be concave up. And so this rate of change of f prime prime of x, I guess I should say, would be positive. It's actually getting faster the more you're throwing it down. The height and base are increasing. Is the rate of change of the area positive? It's definitely positive because both dimensions are going out, and so our area is going to be getting bigger. The height and base are decreasing. Is the rate of change going to be positive or negative? This is going to be negative. You may think that it could be like a negative makes a positive situation, but that's just not how it works. So let's get right into some problems. Let's first start with differentiating implicitly these formulas. We're going to do all of them with respect to t. So take a second, pause the video, and do that real quick. Okay, so this first one is just going to be dA dt equals 8 pi r and then dr dt. Remember, anytime we're differentiating and our variable's not we're differentiating with respect to another variable, and this variable is not said variable, we have to have d that variable dt or dx or whatever it may be. We did that when we were differentiating with y, right? It was like dy dx. Same thing happening here. It's just we have an r and a t. For volume, it's a little bit more work. We're gonna have dv dt. That part's pretty easy. But the second part, we're gonna have to use a product rule. So we're gonna have to treat this as one function and this is our other. And so let's take the derivative of the first. So that would become 2 pi r and then a dr dt. And that's times height, right? This height here, plus, and then now we're gonna have this derivative, or we're gonna keep this the same, and then do the derivative of the h. So that's just dh dt. And there you go. So you see, if we were to do something and we're trying to figure out the rate of change of a volume, we would have to not only know R and H, right? We'd need to know R and H, but we'd also have to know dr dt or dH dt. So keep that in mind. This is also where we want to talk about things being constant, because if we know the volume's constant or the height's constant or the radius is constant, whatever it may mean, then that's going to set one of these equal to 0. So always watch out for the word constant versus variable or constant versus changing. We can even do this with a right triangle ratio. So for example, in this case, we have cosine of theta equals x over 15. If we're doing this derivative, again, with respect to t, we have a couple different ways we can attack it. So way one is saying, hey, let's just take the derivative of both sides. This gives us sine of theta, sorry, negative sine of theta, and then times d theta dt. And then that equals, well, the fact that this is x over 15, you could also just rewrite this as 1/15 x. So treating that 15 as a coefficient. And so this would just become 1 over 15 dx dt. Now think for a second that this may be a little bit of a problem in the fact that not only do we need to know d theta dt, which sometimes we're trying to solve for, we also need to know dx dt, and we need to know sine of theta. So there's a lot of information we might need for a problem like that. We might not have all of that. So instead, we could think about how could I deal with this and just solve for theta? Let's say I just want d theta dt. Well, I might want to solve for theta before I do anything. And so I would first, to solve for theta, I would take the arc cosine of both sides. And so this gets me theta equals the arc cosine of x over 15. Now, again, not great, right? Because now when we're doing d theta dt, we're going to have to deal with an arc cosine, but we have this already isolated. And so if we do this d dt, then this looks like d theta dt. I'm running out of room, so I'm going to do it d theta dt equals, and then we say, okay, what's the derivative of the arc cosine? Negative u prime. So what's the derivative of x over 15? That would just be negative 1 over 15. And then you still need that dx dt though. And then divided by the square root of 1 minus x over 15 squared. So we can see that while this is still super ugly and, you know, that's gross to deal with, in this case, we only need x and dx dt. We don't need that additional piece of like, what is your sine of theta? So that's a little bit nicer to deal with, but sometimes the equation's a little uglier. Let's get into some problems. Well, let's actually look for guidelines first, right? So we talked about this a little bit the other day, but drawing a diagram and labeling changing, unchanging, static, we talked about it as constant values with exact numbers, and labeled dynamic values with variables. We're going to use a lot of geometry, some algebra, and a lot of trig. Write your equation to fit it, differentiate both times with respect to time, or both sides with respect to time, and identify rates using the words. So here we have a 25-foot ladder leaning against the house. The base of the ladder is pulled away down from the house at a rate of 2 feet per second. So it's being pulled away from feet per second. How fast is the top of the ladder moving down the wall when the base is 7 feet from the house? So a couple things here. Let's kind of figure out what we know. So it's not telling us it's a right triangle, but we're assuming this house isn't like leaning in any way. And so we can consider this a right triangle here in our diagram. We're also told that this is 7 feet away from the house. And so we could quickly do a Pythagorean theorem to say a squared plus 7 squared equals 25 squared. And I believe this is a Pythagorean triple, but I could be wrong. I think this is just 24 squared. Yeah, it's a is 24. If you do the math there, you're gonna get a is 24. And so this is very helpful because now I know exactly what's going on with all my dimensions. Then we're not talking anywhere in here about area of a triangle. We're just dealing with rates. And another piece that we're kind of not explicitly told, but it's saying that the ladder is 25 feet. And if we're to pull the ladder away from the house, our ladder isn't going to change. So if we want to call this side length A and this side length B, and this is C, we know that essentially DC dt, or essentially the rate of change with the hypotenuse is not going to change length. And so this becomes dc over dt equals 0. Now, again, let's go back to our Pythagorean theorem equation. A squared plus b squared equals c squared. We kind of realize, all right, well, dc dt is 0, so that's great. We're told what db dt is, right? How fast is this moving out? And we're trying to figure out dr dt, which is what they're calling this r. We're going to call it a, so dA dt. So if we take the derivative of this with respect to t, or essentially figure out how is this changing with respect to time at this instant, we can just differentiate. So this gives us 2a and then dA dt plus 2b dv dt equals 2c dc dt. And then we say, hey, let's plug in what we know. Okay, well, dc dt is 0. So this entire right side of the equation becomes 0. Doesn't matter what c is. If this rate of change is not changing because it's a ladder and the ladder's not getting shorter, we're good to go. If you're like, well, how do I know the ladder's not getting shorter? It would tell you something about the ladder's length and everything like that. We know a is 24, so this becomes 48 dA dt. And then we know b is 7, so this becomes 14. And then dB dt, we're told that moves at a rate of 2 feet per second. And again, this is saying away from the house, which means that this length is increasing. And so this is going to be a positive dB dt. Whereas what we're solving for, dA dt, is going to be negative because it's sliding down the house. And so that's going to be decreasing. And so if we want to solve this, we would get 48 dA dt equals negative 28. And then we solve and get dA dt is equal to negative 28 over 48. I'm going to simplify that just a little bit. We can take out what, a 4 out of both of them. That gives us negative 7 over 12. And again, this is we need to apply context here. So what does this mean? Well, let's use our units. Negative 7 per 12 feet per second. And there you go. If you want the full sentence, you would say the top of the ladder is moving down the wall at a rate of negative 7/12 feet per second. I think if you were to show this and label your diagram, you would be fine. I don't think you'd have to worry about writing, like there's not really a given time. It's like as the base is 7 feet from the house. You could say something along those lines, but I think if you just solve like this, we're okay. All right, let's move on to the next one. So here, read the problem, take a second, see if you can set up an equation. Okay, so here we know essentially the mount is 300 feet from the launch pad, and as this rocket's going up, this distance is not changing. It's still going to be 3,000 feet, so that's kind of our constant, right? And again, it's not explicitly telling us, but you need to say, all right, is that changing? The rocket is rising vertically at a rate of 800 feet per second when it's 4,000 feet high. So this is a moment in time at the 4,000 feet mark, we can apply this rate. Notice we're not applying that ahead of time. We're only applying that here. We're trying to figure out how fast is the camera to rocket distance changing. So we're essentially trying to realize how fast is C, or the hypotenuse in this case. So the camera needs to pivot as the rocket moves. We essentially have this amount of information. We know this is 3,000. We know this is 4,000. And this is telling us it's a 3, 4, 5 triangle. If you don't know that, we're essentially just doing 4,000 squared plus 3,000 squared equals C squared. And so we say, hey, C has to be 5,000. If you just take the square root of both sides, you're going to be set. What we don't know is dC dt. So we take this information, we know essentially that C is gonna be 5,000 at the 4,000 mark, right? When it's 4,000 tall. And we say, okay, well, let's do our equation. Again, A squared plus B squared equals C squared. And now we just differentiate. The great part here is let's call this A and let's call this B. In this case, we can I'm doing it to show you the work, but dB dt is 0, right? That camera is staying constant away from the rocket, and so we don't really have to worry about that. But if you want to keep it there, you can. A is 800 at this time. Or sorry, A is 4,000, dA dt is 800. So this becomes 8,000 times 800 plus 0. Again, I don't care what B is because dB dt is 0. And then 10,000 dC dt. All right. All we have to do at this point is we're just going to multiply 8,000 times 800, and then we're going to divide by 10,000. And that gives me dC dt equals 640. And then let's make sure we have the right units. 640 feet per second. And again, not the worst thing in the world here. This is just Pythagorean theorem. This kind of makes sense with our context, right? We always want to figure out, does the sign make sense? This sign does make sense because our rocket's going up, and so that means the distance away should also be going up. It's going to be kind of going up at a quicker rate the higher we go, because you're going to be looking up higher and higher and higher. Cool. All right, let's try to move away from triangles and move into cones. What exciting times. Looking at cones. Love it. All right, so for this one, sand is poured on a beach, creating a cone whose radius is always equal. Ooh, look at this. Look at this always we're gifted with. That's telling us that we have this kind of constant relationship. Is always equal to twice its height if the sand is poured at a rate of 20 inches cubed per second. Okay, so if we're dealing with 20 inches cubed per second, what that's telling me, because this is inches cubed, is this is dealing with volume. And so this is going to be dV dt because of the inches cubed per second. So the per second tells me the dt, the inches cubed tells me dV. We want to know how fast is the height of the cone, height of the conical pile changing at time at 2 seconds. So we know the radius is always equal to twice the height. And so we also can say, all right, well, we can use that when we're dealing with how much this is changing. And so if we know that this is 2, if the radius or how fast is the height changing at the time the height is 2, sorry, I said radius, I meant height. This gives us r equals 4. And we can also talk about dr dt, right? We have this relationship. This is always a true statement. And so if we differentiate with respect to time, we know dr dt is equal to 2 dh dt. And again, we're trying to figure out how fast is the height of the conical pile changing. So because this is a cone, our formula is usually v equals 1/3 pi r squared times height. However, we want to essentially figure out this all with respect to height. So we'll say, hey, r equals 2h squared. So we're going to replace, or 2h. So we're going to replace this r with a 2h, and then we're going to square it. And so now this gives us V equals 4/3 pi h cubed, which is great for a number of reasons, but also kind of looks like a sphere. We're going to change this with respect to t. So we're going to take this derivative, and this gives me dv dt equals, we can just use the power rule here because we only have one variable, which is why we wanted to sub this out in the beginning. 4 pi r squared dh dt. And again, I don't think this one's too bad because, hey, this is 20. So we'll just sub this in for 20. And then 4 pi, what's our height? Well, hey, our height is 2. And then dh dt is going to be what we're trying to solve for. And so this simplifies down to just 16 pi. Let's divide that over and get dh dt is equal to, what would that be? 5/4 pi. And this is in inches cubed per second. And so this would be inch per second. If we want to do part B, where it's 6 inches instead, all we have to do is replace this with a 6. Everything else stays the exact same, which is great. Then this gets me, what is that? 144? Yeah, 144. So 20 divided by 144 pi is 5/36 pi. Oop, I almost put the 36 on top. We can see that this is getting slower, essentially the higher up we get, which kind of makes sense because if you think about a cone, right? Let's see if I can draw a cone. So if you think about a cone, as you're getting higher, right, the radius is getting wider, and so that height isn't going to change as quickly because you have more area to pour your sand, right? So this volume is going to affect it a little bit less the taller and taller you get with your cone. It makes sense because, like, think about if you've ever I was gonna say like filled up a cone, but that's a weird statement to say. It fills up really quickly at the bottom and then takes a while to fill up at the top. If you ever filled up like a bowl of soup, the bottom fills up really quickly and then you can like put a bunch more soup up at the top. Okay, let's try this next one. All right, so we're talking about water draining from a conical tank. Again, vertex down. Water is draining, and so this rate is going to be what? Is the volume increasing or decreasing? Well, again, it's decreasing because it's draining, so that means negative. So this is really a -2. The tank is 16 meters high, and the top radius is 4. We're trying to figure out how fast is the water level falling. So how fast is the water level falling? Water level means we're talking about height. So we're really trying to figure out dHdt. And we need to know when that's 12. So if we know the volume is equal to 1/3 pi r squared times our height, we might try to have we might try to solve, essentially just take the derivative right off the bat, but realize we have a couple issues. If we take the derivative right off the bat, as we saw in kind of one of the warm-up problems, we would need to know both r and dr dt. And we could use a similar triangle here, and we're gonna have to use similar triangles coming up, but and say, hey, this is 12 and this is whole thing 16. And so what's this radius? But the problem is we don't also know what dr dt is. And so even though we could figure out what this radius is at this point, The fact that we don't know dRdt is a bit of a problem. So instead we say, okay, well, this tank always has this ratio of 16 to 4. If you look at this tank, it's 16 meters high, the top radius is 4, and so that ratio is going to be there no matter how much the water level sinks, right? This is all going to be similar triangles, so we're going to keep that ratio no matter where we're at. So if the height's 16 and the radius is 4, that means the radius is equal to 1/4 the height. And you may think, well, I'd rather use h equals 4r instead, because that's easier to work with and fractions are scary. But remember, it's asking for dH dt, right? This is kind of our end product. And so we're going to need to replace h, we're going to need to replace r, not h. So what we're going to do here is we're going to essentially replace our r with our h. This becomes 1/3 pi times 1/4 h squared times h. And so 1/4 squared is 1/16. That becomes 1/48 pi. I'm just gonna put the pi on top. H cubed. Super gross. So now we're gonna take this derivative with respect to t, because we're trying to find this instantaneous rate of change at this specific instant. Notice the time's not mentioned here at all, but we're trying to figure out like when specifically this is happening, and so that's why it's d dt. So this gives me dv dt equals, and again we're going to just use the power rule here. This is pi over 16 h cubed, or sorry, h squared dh dt. We're already told dv dt, right? We were given that right at the beginning of the problem. That's -2. Pi over 16 is, it's still pi over 16. Way to go, us. The height's 12, so that'll kind of deal with that 16 piece. And then dH dt. 12 squared is 144. 144 divided by 16, I believe, is 9. Yep. And so this becomes -2 equals 9 pi dH dt. And so dH dt is equal to -2/9 pi. Look at us go. Last thing we need to do is make sure we use the right units. And so this should be -2/9 pi meters per second. So the big lesson with this problem is really try to figure out, like, okay, if I were to differentiate this, what information would I need to be able to solve? And the fact that we had to, if we just used this as it was and differentiated and, you had to use the product rule, we need to know R, which we could find, right? That's possible with similar triangles, but we'd also have to use dRdt, and that's not information we had. And so because we had to have both of those pieces, we have to say, hey, let's back up. Let's do something completely different. All right, let's try another one. And this is talking about shadows. So here's your similar triangle problem that I know you guys really love. I know this similar triangles, obviously a favorite topic in class. Suppose a 6-foot tall person is 12 feet away from an 18-foot lamp post. Okay, so 18 feet, person 6 foot, 12 feet away. So lamp post is shining light, and you're gonna have a shadow. Look, these are my light rays. This is 12 feet away. And the person is moving away at a rate of 2 feet per second. 2 feet per second. And we're trying to figure out at what rate is the length of the shadow changing. So we kind of need to know this piece, right? And we know that rate that we're dealing with, but we don't know the rate of the length of the shadow. So again, we have similar triangles here. And that's really nice to deal with, because if this is 18 and this is 6, then we realize that the heights have a ratio of 1/3. So we know this is 1/3. Oh, sorry. We know this is a 1-to-3 ratio, and this 12 is probably going to throw us off. If we want to actually solve for all this, you can see I did that work in the green right here. That tells us this length is 6, but it doesn't really help us like solve the problem at all, because the rate of change of the shadow is only dependent on this rate moving right here. And so what we do instead is we say, okay, well, let's set up a ratio. Let's, instead of calling this 12, which is completely unnecessary, let's call this X, and let's call this Z. Or let's actually just do A and B, because why not? A and B. And so let's erase all this and all this garbage over here. And let's say A and B. If we want to set up similar triangles, for those of you who don't remember how similar triangles work, we essentially say, hey, these two triangles are similar because these are both perpendicular to the ground. And so we have similar triangles by AA similarity. And so we say, okay, well, if this is 18, this little guy over here, let's use red so you can see it. This little guy here is 6. It has a height of B. This whole height for the big triangle is A plus B. And so we can set up a ratio. I personally like to do 18/6, but let's just do it triangle to triangle. So base over height equals base over height. And if we cross multiply, we can get 18b equals 6a plus 6b, which simplifies down to 12b equals 6a, or a equals 2b. This is much easier for us to deal with because we can kind of figure out this as a like derivative really quickly, right? If we take the derivative of this with respect to time, we're dealing with the way A changes, which we know is 2 feet per second, and can compare that to the way B changes, which is what we don't know, right? So we already were told dA dt right at the beginning of this problem when it said 2 feet per second. And so again, that's A because that's the length that this piece was increasing. We're moving away, and we don't know the rate that this shadow is increasing. And so if I take the derivative of 2b equals A with respect to time, I get 2 dB dt equals dA dt. And so this gives me 2 dB dt equals 2. And so dA dt, oh, sorry, dB dt equals 1. Questions with that, please let me know. But if we try to do any other piece with similar triangles, it's going to be a bad time. We also want to figure out what is the rate at which the tip of the shadow is changing. If we're talking about the tip of the shadow changing, it's just the rate of, it's essentially dA dt plus dB dt, because it's the two rates added together. It's the rate that this length is changing plus the rate this length is changing. And so our final answer would be 3 feet per second. All right, gang, that's all the time we have. Hopefully that was helpful. It worked through most of the notes that we're going to get. And as always, if you have any questions, please feel free to reach out. Have a good one.